Okay, so thank you, Julian, for looking it up. The definition, at least in Silverman, of isogeny is that it doesn't have to have finite kernel. So either it has finite kernel and it is surjective, or it's a zero map. So this is basically the same like what we did. We just defined the isogeny to be not the zero map, and then because Anton said it, we included the zero map. But the definition in Silverman is that an isogeny, that the zero map is also already an isogeny. There's also the term of n isogenies, where n is the size of the kernel. So that's where then it has to be the finite kernel. So we could also just define the isogeny to be an n isogeny and then take the zero map additionally. Okay, so we proved that if we have complex multiplication, then we have then this is our elliptic curve, and we have an m that multiplies from here to here, for example, and this is always an imaginary quadratic number or an integer. Well, but then it multiplies on this line, basically. Okay, so in Julian's lecture, we also had the relation between the elliptic curve as an algebraic group and the torus, and we also had the relation between the J invariant of the elliptic curve and the J invariant defined by some modular functions, or at least we had a glimpse into that topic. And the interesting, at least what I find interesting thing about elliptic curves is that there's basically two worlds. That there's the algebraic world. We mostly covered the algebraic world with the points and the rational points and the algorithms and so on, but there's also the analytic world, which was the elliptic curves over C and the J function as a modular form, and holomorphic maps and the upper half plane. And what I also find a bit funny is that usually people in those worlds don't really talk to each other, so that there's, in my opinion, not enough research that takes both into account. But what we'll do now is first maybe a small remark. The J invariant in the analytic world is a modular function on the upper half plane. And if you don't know what modular function is, just replace modular by nice. Or as a tribute to the analytic number theorists, very nice, actually. Because I think usually when I listen to talks about modular forms, it always sounds like magic. They just put some numbers in some series and then something magical happens and everything works out and it's very nice. So this is why I would say modular function can also be called a very nice function, because it has many nice symmetries and many nice properties. But for now, it's not necessary to know exactly what it means. When we use some properties of the modularity, I will just say it. So the theorem, I think it's maybe also called one of the main theorems of complex multiplication, but not the main theorem. So if Z0 is in the upper half plane and is a CM point, so remember, this meant we have an elliptic curve with complex multiplication, where in the analytic world, so on the torus, we have a map that's multiplication by this number. So this is a CM point. then j of z0 is also an algebraic number. So we proved before that z0 is an algebraic number of degree 2. So we can just find A, B, and C. Such that this holds. And we can also make sure that A is positive. Do we need that? Yes. If not, we just multiply by -1. And then we define a matrix. So either if A times C is not 1, then we take this matrix. And else we take this. And so remark, if A times C is not 1, if L times C is 1, so this means A times C is 1, then this means A and C are 1, because A is positive and A and C are integers. So this means A and C are 1. And this would mean that what do I want to say? No, I want to say something else. So if this is the case, the determinant of M is not 1. So small side remark. If A and C are 1, then the determinant of 1 minus 2, 2b plus 1 is 2b plus 1 plus 4 plus 2. It's plus 1. Yeah. Now I want to know what I want to say. So if this was 1, then this meant that this would mean that B is minus 2. This would mean that Z0 squared minus 2Z0 plus 1 is 0, which means that C0 is 1, which would contradict this. So this is just a small side remark that the determinant of this matrix is not 1. And the determinant of this matrix is also not 1 because it's B times 0 minus A times C, and A times C is not 1. Okay, but this is just a side calculation. Okay, since J is a modular function, and j of mz is also a modular function. We take this as a black box. Then we can show that they have to be algebraically dependent. So this also comes just from the theory of modular functions. This means just we have a polynomial in two variables, and when we plug in this and this, it becomes 0, and the coefficients of the polynomial are integers. So this is a polynomial. Okay. So now we want to use this to show that we actually have a polynomial with integral coefficients only in j of z0 then, that has only in one variable where j of z0 is a root. Okay. Our first claim is that the coefficients of this polynomial only depend on the determinant of m, and they are all integral. Or these are two different claims. Remember, m just consists of the coefficients of the minimal polynomial of z0. And second claim is, now we will get to the second claim. Because then we will change a bit this polynomial, and then we get a new polynomial, and then we want to prove that the new polynomial has integer coefficients. Okay, so let this curly m with small index m be the set of matrices that are invertible and 2 by 2 matrices and have determinant 1. And integral coefficients. Okay. So now we need another black box, modular forms theory. If we consider this set, this is an invertible matrix because neither A or D is 0, as we will define it here. And the black box will be that this set characterizes the sublattice of a fixed lattice of index m. So we have a lattice of index m, and these, the sublattices of index m can be have a one-to-one correspondence to this set. And now this only depends on m, as you see. So here we go through all a and d integers that multiply to m, and b and d are also bounded by m, because d is bounded by d, b is bounded by d, d is bounded by m. All are integers, so this set is also finite. Characterizes the sublattices of a lattice of index n. And these are also the finitely many, because finitely many, as I explained, SL2Z orbits of this thing. How do I write that down? Finitely because of this. Okay, and as I said, there are only finitely many of such matrices. And so what we can do now, start a new board. Oh, this is getting very analytic. So what we can do now is run through all left cosets of this. So left, just because we multiply this matrix from the left, which feels a bit strange, but it's nothing different than multiplying from the right, just from the left. And well, this looks more complicated than it actually is. Because what do we do here? We basically kind of factorize this polynomial, and know that it has to be yeah, how do I explain this? So our polynomial p was this here, where we said this is the polynomial that describes the algebraic dependency of j of mz and j of z. And now we found a way to kind of describe all the cosets of the matrices that are invertible and have the determinant m by sublattices. Okay, why is this well defined? Well, this is actually again part of this niceness or very niceness of the functions, because we can multiply here by SL2Z, and for modular functions this is not a problem. Okay, what did we gain now? So we gained now, we made a polynomial in one variable here, and our j of z that we still have. And if we write that down, we can actually show that the coefficients only depend on this m. So let me maybe another remark, because this is just a small black box. I didn't define how we actually multiply matrices with complex numbers. Of course, we can multiply them component-wise, but here we do something differently. So the matrix that we have here is this AB0D times C. This should just be AZ plus B over D. And if we plug that in here, then we have so first this. So this is just this, and now we have to go through all the m primes. We saw that B goes from 0 to D minus 1, and then we go through all A, D, which are smaller than M, and multiply to M. So A, D is equal to M, and D is positive. Yeah. Yeah?
So that our M primes don't need to have the form AB0D, right? Because they have an
yeah, that's what I wanted to say here. That this MM star is just the finitely many cosets in this MM modulo the SL2 Z actions. Genau, these are the finitely many SL2 Z orbits of M, so everything that can happen in there. So this is the same as we do this. Yeah, sorry, this is a lot of analyticness, but it will get more algebraically soon again, or at least more computationally. Also algebraic. It will get more algebraic. Okay, what can we do here now? Another black box is that the modular J function, that's the J invariant in the analytic world, has a nice series expansion. And we can do this. Keep this here. Where this Q is just a way to write this, e to the 2 pi I z. The zetas are roots of unity, and the Cn are integers that come from this series expansion. And it is, well, not so hard, I think, to show that all those are integers, but too much for here. And you should just remark that this starts at -1. So the expansion is something 1 over Q, and then 744, and then something with Q, I think, I don't know, just roundabout, and so on. I only know the first two terms. Okay, so now we're actually finished with the claim above, because here this doesn't depend on this matrix M anymore. It only depends on A, D, and B, where we run over all A, D, and B. Yeah?
What is the exponent of the
B times N. Yeah. Yeah, it's a bit hard to differentiate between the D's and A's. And also this is of course a D. Yeah. Okay, so now we show that this is independent of the matrix M and only depends on M, because here we run up to M, so everything still depends on M. M basically also only defines how far we have to go. So it is independent of this M that we chose at some point, and we have a polynomial in one variable that will vanish for j of z0. So we almost finished. We only have to show that the coefficients here are integers. This is actually not so hard. I wanted to give it as an exercise, but I'm not so sure if we will maybe give an exercise sheet. But the idea is, I will tell you the idea and then maybe it will be an exercise. So the idea is that those are roots of unity, and well, if you look at what kind of products we take here, this will just be a permutation and reordering of roots of unity and powers of them. And if you order them in the correct order and use some Galois theory, and use that if you take a Galois automorphism and throw it on there, then it should not make a difference because it leaves the rational things alone. This together with some combinating arguments should give that all the coefficients are integers. All the coefficients in front of those, and then you can follow that the polynomial itself has integral coefficients. So P is independent of M. P has a root at z0, and exercise P has integral coefficients, and altogether this means at j of z0. J of z0 is an algebraic number. So indeed, it is also true that j of z0 is actually an algebraic integer. This is, well, I will do some things that kind of go in the direction of proving that it's an algebraic integer with some more black boxes, so this is not too hard. But what's interesting is also the inverse is never an algebraic integer. So keep in mind that we're always in the complex multiplication case here, because we have this z0 in the upper half plane. And we proved, or almost proved, that the J invariant of this CM point is an algebraic number. It is possible to prove that it's an algebraic integer, but its inverse is never an algebraic integer. And this is a recent result, well, recent for math standards. It's in this century. And I know all the people who proved this. But this is really, so it was a big thing from this century. Huh? Yeah, it was from, I think, well, it depends on the date where you put it on the archive or the date where it's in the journal. I think it was something like 2015, so a few years ago. I'm always scared that this locks us in and we will not get out. Huh? And what do you do then? Then you call someone. And if no one has a phone? Huh? I also don't have a key here. Yeah. And I think from the inside you cannot use a key.
You can open it.
We just destroy the door. We can maybe jump out the window. So we come back to the algebraic world with a definition. So we have an order in an imaginary quadratic number field. So this is this can be an endomorphism ring of an elliptic curve. Oh, and I don't know if I wrote that somewhere. If O is an order and it's the endomorphism ring of an elliptic curve, then we say the elliptic curve has complex multiplication by O. So now we want to consider all the elliptic curves that have complex multiplication by O. And the question is, can this set be empty? How large is it? Can we find out how large it is? And we also define this polynomial here. maybe we define it as the set of J invariants, so that we don't have to handle isomorphic elliptic curves and don't get double factors. So this is every factor appears with multiplicity 1. Okay, and we call this the Hilbert class polynomial. And the question is basically, what's the degree? And in my master's studies, I attended 2 lectures that were particularly great. Namely, one was a lecture on Diophantine approximation. That's basically where we showed this Diophantine approximation theorem. There was a lecture basically going around this theorem for 1 semester. This was very great. And the same person, I had a lecture on binary quadratic forms and quadratic number fields. And well, kind of one of the goal of the lecture was, amongst other things, to show the connection between the class group of a quadratic number field and binary quadratic forms. And this is also where this comes in, because this is also basically the class group. And the class group is the holy grail, the queen of everything. And that's what I will write in the following theorem. Oh, and this person that gave this lecture is Clemens Fuchs. So hello to Clemens Fuchs. Very nice lectures. Okay, so it's only a remark. So what does that mean? Oh, and another remark, which is also, so both is very amazing, I think. It's a polynomial with integral coefficients, and its degree is the class group of this order. I hate those doors. I hate those doors. But so if you think about it, it also makes a bit sense. It's at least as a gut feeling, this makes sense. So if you have a curve with complex multiplication by the ring of integers, and you want to see if there are more curves of complex multiplications by an order. Oh, wait, let me. Maybe I have to change my explanation. No, maybe I don't have the good words for my explanation, but if we look at the class group, then this consists of ideals that kind of help us construct this ring of integers, and so it kind of makes sense that every one of those basis ideals gives rise to one elliptic curve or one isomorphism class of elliptic curves with complex multiplication by this O. So the ideals in an order, you can look at them as sublattices of the order, and in the class group you have some equivalence relation which kind of corresponds to the equivalence relation of being isomorphic in here, being or having the same J invariant here. So it makes sense that ideals in this class group correspond to different elliptic curves with the same order as endomorphism ring. Yeah, I can still write down the kind of main theorem of complex multiplication, which is basically everything I just said put together in one theorem. We have a maximal order of discriminant D in an imaginary quadratic number field. So the maximal order is the ring of integers, but this is actually not important for us. Let L be the splitting field of the Hilbert class polynomial over Q squared of D. So just the field that contains all the zeros or all the J invariants that appear as J invariants of elliptic curves with complex multiplication by this O. Then the degree of H is the class number, as I said before. There is an isomorphism between the class group and this Galois group. And what I find so crazy, this has integer coefficients and is irreducible. Well, okay, so it's not so crazy because we already know that the J invariants are algebraic numbers of degree 2 and is irreducible. But without the whole theory behind, it's just crazy. If you hadn't known how we constructed those, or not constructed, how we proved things about this J invariance, then this would be crazy, I think. So when I heard this the first time, I didn't believe it. Okay. So, yeah, a nice corollary from this is that if we have a number field which has a ring of integers with class number 1, I think there are 13 of those, then the J invariant is an integer. Because then the degree of this H is 1, and it has integral coefficients, so the J invariant is an integer. Okay. And so I will do this next time, but as a teaser, I love this example, or it's not an example, more of an anecdote maybe. Y is e to the pi to the minus 170 63. Almost an integer. This we will see next time. Okay, thank you very much.